What method have you used to control current?
An H-bridge.
Okay, sort of. Control current. I'm going to write that down because we're going to come back to that. H-bridge. It's not really the way you control current, though. Bridge. Right? It reacted to current. What is an H-bridge? An H-bridge is a bunch of switches in the coil. The H-bridge is more like your motor, or a way to get current to the motor, right? It's a bunch of switches.
Can't you change the...
So you can move it around, you can change it to different coils, and you can make it go back and forth, but that's not how you adjust to control. So let me add one more thing in here. Control amount of current.
Encoding in a PWM?
Yep, that's, well, okay, so what are your two big methods? What's the simpler method than PWM? PWM takes a lot of stuff. What's the simplest method to control current?
Resistance.
Resistor.
Right. So V equals IR. Right? Or I is equal to V over R. So the simplest way in that motor would be if you knew, let's say you went and bought a motor, or you selected one out, you haven't bought it yet, but you are solving this application and you find a motor on the Applied Motion Products webpage. They're a great manufacturer right down in the Bay Area. Applied Motion Products, you find a motor, you look through all the motors, you see all these different windings and sizes, but you're looking at speed torque curves, and finally, like, here's one that solves this application. Aha. Once you see the motor that has the speed and the torque, what's the one thing you're going to want to look up then? In order to get that speed and torque, what do you have to do? You're going to look at the conditions that they develop that speed torque curve. And two of the key conditions are voltage and current, right? So what you're going to see is, oh, if I want to use that motor, I need to provide it 3.6 amps of current to get that speed torque curve in order to get that amount of torque. Does that make sense? So now it's up to you to control the amount of current to that. If you give that motor, let's say you choose a motor. Here's our motor, and the motor needs 3.6 amps to go through it. And that gives you torque. So what if you gave it 3.8 amps? What's going to happen?
Have more torque?
It would have more torque because it's an electromagnet. It responds to current. What's the downside? What's it going to do?
It'll heat up more.
Yeah. You're going to burn it up. If you put in 3.8 amps, if they could have, they would have put in 3.8 amps. They have incentive to give you good speed torque curves. That's what they compete on. And they said, no, you got to give it 3.6. What if you don't have 3.6? What if you give this motor 2.6 instead of 3.6? Now what happens? Well, speed torque curve, you're looking at speed torque curve. This one was 3.6. Here's 2.6. Here's 1.6. So right? So you're starting to see that torque versus speed, that current is proportional to torque. No surprise there. And then also going along this axis, the higher voltage you have. So we're starting to get from this, and we'll touch on this a lot more in closed loop, that generally current is proportional to torque, at least within the constant power range, and voltage is proportional to speed. Okay, so you're going to be adjusting some of these things, but you can't just put more current into the motor because it burns out. So that doesn't work. In order to get 3.6 amps through this motor, just with using V equals IR, if you had a resistance of 1 and you put on 1 ohm, right? How much voltage can you put on this thing to get the right amount of current?
3.6 volts.
Right. Right. We don't do that. 3.6 volts gives you a curve. Let me show you what the curve looks like for 3.6 volts. There. That's what 3.6 volts looks like. When you go to look for these curves, they're going to have voltages on them. They're going to say this one is 48 volts. This one might be, you know, that they might have another one out here that is like this, and that one might be 80 volts. Think about electric vehicles. When they made electric vehicles, you guys have any experience with that? What's the voltage they're running in electric vehicles?
It depends, doesn't it?
Yeah, it depends. What are some of the ranges though? Different.
300 to 600.
Yeah, like in the big buses and stuff, they're running 300 and 600 volts, right? They're not. What's the voltage in your battery in your car?
12.
12, right? When they first came out with them, they were running 40 to 50 volts, and there's a key transition at 40 volts. You go over that, you have to start playing with all sorts of safety issues, right? People are happy as long as I think it's 42 volts and below, you're happy. But as soon as you go over that, safety becomes a real issue. And so I guess my big general point is V equals IR, we don't use that as a method of controlling current. You don't vary the voltage to control current because we don't run motors at 3.6. We're at 36 and high voltage. Why do you want high voltage? Because it's an inductor. You've got to drive the current up in the inductor. And if you don't have voltage, you know, the LDIDT thing, you don't get, you get this. So that's no good. So what do you use? PWM. I want to do the H bridge real quick because I think you've got to use that and show you what's key about this. So an H bridge is basically a series of transistors. I could draw them as switches. I'm going to, hold on, I'm going to undo that. I'm going to do, I'll make our motor green. Okay, there we go. So H bridges are a series. I'm just going to draw BJT. You don't have to draw this perfectly right now. Now I'm going to avoid. I'm going to stop with the electrical stuff. And the first thing I'm going to do, normally I would just put ground and V on this, and I want to break you of that habit. From now on, you will never just draw ground or voltage in the air. You need to do this. It needs to do that. We need to start drawing circuits. In electrical, you can just draw, you could have just done that symbol and called it good. But the trouble in mechatronics you're going to find really quickly is that you have multiple voltages driving different things. You have 24 volts for sensors. You'll have 5 volts for electronics and microprocessors. And you need high voltage for motors. And so we have multiple power supplies, and we're going to have multiple grounds and multiple ground schemes. So no longer do you just get to draw that ground in the air. From now on, you need to show what power supply and what ground, and that's just simply doing what I did. So there's, you know, this is V bus. And generally the bus voltage is different than VCC. Bus voltage means, oh, that's our 600 volts DC that we're going to put to that motor. That's the high voltage. Now, the reason it's high voltage is because we're running an inductor. So what's an H-bridge do? There's one key thing that an H-bridge allows us to do with the motor. We wouldn't need one if it weren't for the fact that if we want current to go, I know you guys have learned this, but if we want current to go this way through there, then you're going to turn that switch on and that switch on, and you're going to leave this one open, that one open, and that one open, so that current would flow. You can see it, track it through, out of the power supply, in through. We're closing that switch. That's a transistor. That's a switch. We went through the winding, current flow that way, and then I bring it all the way back. Get in that habit of showing that circuit, okay? So the key, though, is that gave it positive north-south energized to the winding, and that makes the motor go that way. What else do you want to do, even in your extruder? You want the motor to go
Backwards.
backwards, right? So if you're going to make a motor go backwards, you need the ability to turn on and off transistors. So if you want it to go the other way, I'll just draw it the other way. If we're going this way, then current's going that way, and we're going to open the other set of transistors. Transistors can switch on and off really, really, really fast. And so this is happening at kilohertz or faster, which is about the right rate you need to do switch motor windings to get it to turn right at most speeds. So the key to an H-bridge is it allows, it allows for reverse current. You can't do that with V equals IR very easily, right? You need something like this. And so that's what's key. But the great news is that's all you need. Now, the trouble is if I just did this, what I drew here was V equals IR, right? So you need to add one more thing in here. You need a driver. You need something that can do pulse width modulation. And what that means is you need to be able to not just turn that on, we're going to turn it on and off and on and off and on and off. And we're going to count on the fact that the inductor is an energy storage device. And so it's like think about like an air compressor tank or a water tank. You could pulse the water into it, but the general amount of energy storage that's in that tank or air storage, energy that's in it due to pressure or height of water column, that the energy that's in it doesn't change with the pulsing. And that's what we're going to kind of do with this. And what happens then is we'll PWM, what we're going to look for is something that over time, we're going to apply a voltage and we're going to choose a heartbeat to the system. Here's how often we're going to turn the voltage on. But then during that on period, you may have a time where it's on a little bit and off, and then it's on for a little bit. And the key is when it's on, I'm applying a fixed voltage that you chose. That's just, you chose 36 volts for the system or 300 volts. You chose that voltage. You don't change that. What we're doing now is we're choosing how long to leave those transistors on. So you need to, these transistors, where'd they go? Oops, where'd my transistors go? I lost my H-bridge. Oh well, my H-bridge went away. On that, that H bridge, you are really, this on time is what you control with a microcontroller, microprocessor somewhere. You need something that can output a frequency and will turn on and off the voltage to that winding instead of just leaving it on like V equals IR would do. If you want to leave it, so this might mean, this here might mean, that might be 1.6 amps average. This rate here, this rate on the time scale, if we flip it around and put it into frequency, this rate is probably 10 kilohertz to 40 kilohertz is what works good. You want to be above 10 or you're going to hear it buzz because it's in the audible range. So you get it up out of 10, and those transistors can easily change at 10 kilohertz. So that might be 1.6. If you wanted to put 3.6 amps through that motor, then you bump up your pulse width modulation frequency, or actually, I'm sorry, be careful here. The frequency is fixed. The voltage is fixed. You adjust what? For those of you that had it, what is the thing we're going to adjust on this curve?
Width of modulation, I guess.
Right, we're going to modulate the width of the pulse. We're going to adjust the duty cycle of this. So pulse width modulation means we're changing the duty cycle. So what that means then, if I want to run, this might be, see the difference here? So that might be 3.6 amps, that duty cycle. You have control over that from your microcontroller. Okay, so big picture now, here's what you need to go do to get ready to solve this application. This is basically your homework now, is you need to start thinking, processing, and start to choose a motor that can do this. I think you should choose, at this first case, you should choose an H bridge. And I'm going to give you, you can do whatever you want for an H bridge that can do this. I don't really care. What I will do is I have one that I will give you if you don't choose one, or I may give it to you anyway, but you're generally looking in the $4 to $10 range for this one. We're not going to do it with industrial components just yet. I want you to do this as if you were building 10,000 units, meaning cost really did matter to this. Let's use your engineering time and get you inexpensive components. The motor isn't going to get that much less, you know, it's going to be a $10, $15, $20 motor. It may even be for the actual application, there's going to be two motors that you choose. One is the one that really extrudes concrete, that's got 12 foot-pounds. You're going to need to make a bill of materials for what solves this application. Here's the motor, here's the drive that solves the application. The other thing that you're going to choose is a motor that you're going to sit on your desk that's going to do your proof of concept. That's going to be a little thing, you know, comes from eBay. It comes from, I got hundreds of them in the Mechatronics Center. I have hundreds of them in Plumas 112. Motors just kind of fly around, you know, they're commodities at this point until they put good magnets in them. And as soon as they put good magnets in them, then they get expensive.